High-rise fires are a matter of life and death, and as local governments and municipalities struggle with public safety budgets, a new study shows that communities considering cutting firefighter crews may need to take a second look. When firefighters respond to a fire in a high-rise building, the size of the crew on each apparatus is the critical factor in quickly putting out the fire and rescuing occupants. That's the finding of a major scientific study of crew size in high-rise fires, led by the National Institute of Standards and Technology. The study measured the time crews, ranging from 3 to 6 members, took to complete a series of firefighting and rescue operations 10 stories up. Because it takes them longer to get set up, smaller crews end up fighting larger fires and facing more toxic environments than larger crews.
When you get into these high-risk, high-level emergencies, you need more staffing as far as putting water on the fire out, completing the searches, victim rescue, and so forth.
It concluded that crews of 3 firefighters start at a disadvantage compared to larger crews, and things just keep getting worse.
If you're working with a smaller crew size, it's going to take you a longer time to get your task accomplished. When it's life and death and there's fire, it's a matter of seconds. It makes a difference.
The study also determined that sending fewer engines and trucks, each staffed with 5 or 6 firefighters, was more effective than sending more vehicles with smaller crews, even when the total number of firefighters was the same.
It was definitely better to have that 5. I mean, when you had just a crew of 3, you couldn't search as fast, you couldn't get as much search done effectively as when you have the other help with you.
The larger crews can save time by carrying out crucial tasks simultaneously, rather than in sequence. This saves lives, lessens injury to occupants, lowers property damage, and prevents firefighter injuries.
Good morning. We're going to talk now about the high-rise experiments. The high-rise study is part of the multi-phase study on firefighter safety and deployment of resources funded by the Assistance to Firefighters Grants. We began our research back in 2005 with one of the first research grants that was awarded through the AFG, and have continued today with over 4 reports being released, most recently the high-rise field experiments. We have several partner organizations, as you have already heard, with NIST obviously being one of the major, but the other logos of our other partners are there on the screen as well. These are the Commission on Fire Accreditation International, as well as the IAFC and Worcester Polytechnic University. And so with our partner organizations, our overall objective through all of the multi-phase studies has been to provide information, provide science, provide tools to decision makers so that you can better match resources deployed to the risk event to which firefighters are responding. And so knowing that that better match of resources to risk can lower or decrease the negative outcomes in 3 areas. First of all, civilian injury and death, firefighter injury and death, and property loss. And so throughout all of our work, these have been the 3 outcomes that we have been able to maintain, and what our research would do then is deliver less negative outcomes in those 3 arenas. And so the principal objective then, as we get into the study, our principal objective on the high-rise fires, much like in the residential fireground that we began back in 2005 all the way through 2009, was to be able to take a look at the effectiveness of firefighter response on those 3 outcomes that were mentioned. The problem statement then for this particular study would be to deliver empirical data, real science, to be able to inform decision makers about their deployment mechanisms, their deployment size of crews, the number of apparatus in all of these areas. Then the question in the high-rise arena is this: to be able to take a look at, in the event of a fire on an upper floor in a high-rise building, what then is the minimal deployment, the floor, not the ceiling, but the minimal deployment in this environment so that we can have safe, efficient, and effective operations. Now that may sound familiar because it's very much like what we did in the residential fireground that informed then the standard of NFPA 1710, of establishing the minimum, the floor, not the ceiling, if you will, for response to low-hazard residential fireground. And so with high-rise being the other end of that, we've tried to bookend the spectrum of hazards or the spectrum of risk to which firefighters respond. So again, looking at the overall objective of safe, efficient, and effective operations. So in histories of high-rise, you're all familiar with some of these fires, and the history of high-rise has been that these are low-frequency but very high-consequence events. And so in the low-frequency, high-consequence events, some of them that you are most familiar with, certainly the First Interstate Bank, the One Meridian Plaza. Some of you in this room may have even responded, certainly the Deutsche Bank being one of the more recent. All of these presenting some very serious challenges to the overall operational capabilities of the fireground response. So in the experiments, we had 3 variables, and these 3 variables were established: crew size, the deployment or the alarm size, how many apparatus, how many crews were sent in each alarm, and then vertical ascent, whether they use stairs or elevators in the ascent. And so with these 3 variables, everything else in the experiments had to be held constant, so that as we conducted them and we made these measures, these are the only 3 things that changed. That's how we know these are the 3 variables that affect the outcomes, which I mentioned earlier. And so through the overall experiments, we conducted 3 replicates, and we did the combinations. There's actually 16 combinations there, 4 times 2 times 2. With that made up one of the replicates. We conducted 3. We actually ended up conducting 4 because we did a series of shakedown tests to make sure that everything else was held constant, except for these 3 variables. With that being the case, to better define the variables for you, crew sizes, we looked at 3, 4, 5, and 6-person crews, making up the effective firefighting force, or the assembly of the first alarm. Then the deployment size, or the alarm size, we had a high and a low. Now, I'll stop for a moment and tell you here that we used a lot of subject matter experts throughout the United States and Canada to inform us on establishing protocol. And in doing that, we looked at the protocols for a lot of metropolitan jurisdictions. We had subject matter experts from New York, Chicago, Cincinnati, Phoenix, Montgomery County, Fairfax County. And so across the United States, these subject matter experts were able to advise us, and we looked at operational protocols for many of the departments, and that's how we established these 2 patterns. So you'll see the high and low, with low being a 3-engine, 3-truck response, high being a 4-engine, 4-truck response, because this pattern sort of availed itself as we began to look at your protocols and the way that you respond today to high-rise fire. So what made up your first alarm? And so that's how we established then the low and the high alarm assignment. Then the vertical ascent variable, of course, were stairs and elevators. We also, after completing the time-to-task experiments, did a series of fire modeling. So this experiment, the high-rise experiments, were actually in 2 parts. One in the field with firefighters actually responding, some as you saw in the video, with time-to-task measurements, which I'll tell you more about. And then in the labs at NIST, where they used the same fire simulation that you saw some in Steve and Dan's presentation, to model both a slow, medium, and fast growth rate, as well as the potential for fire spread throughout the high-rise environment. So with that, then we had the Fireground Overview. Our scenario was a 13-story building. We had the fire on the 10th floor. It was a commercial building. One of the floors, the 10th floor, was a floor of cubicles, more of a cubicle farm, where the 11th floor, the floor just above the fire, was going to be a series of closed offices and conference rooms. So the series of searches that you're going to see varied between the cubicle farm and then some offices and conference rooms. We also had 2 victims, one on the fire floor and one on the floor above the fire. There were overall 38 tasks that were measured throughout the experiments, and so 14 of these tasks were deemed critical, and those are the ones that we're going to pay some special attention to today, because these 14 critical tasks had to do with the change of the environment in the structure, a lot of which Steve and Dan just spoke to you about. How do you change that environment? Well, first of all, we know we've got to get the fire out, and so putting the fire out is one. And then how the tenability changes based on how long the fire was allowed to grow, how many toxins were released from the combustions, the products of the combustion, into the atmosphere. And so these 14 critical tasks that we're going to be discussing throughout the presentation will be those that are deemed most critical. So the experiment site was a 13-story building in Crystal City, Virginia. Again, the fire was on the 10th floor. We had to go in and do some building preparation. This was a vacant building that had been actually vacated by BRAC or some of the movement of the federal bases throughout the Washington, D.C. metropolitan area. So we went in and built in cubicles that could be searched. We built in that cubicle farm that I spoke to you about. We also had to simulate fire and smoke. We did not do any live burns in the building, but we did have simulating. Bullock's joined us as one of our in-kind partners to be able to simulate fire and smoke. And so we did create as best we could real atmosphere, the real tenability, real look of the fire upon arrival of the crews. Now, you can see there in the background, and you might imagine as we were informing or orienting the crews every morning that we got a lot of eye rolls that it was going to be this real, but this is what they actually saw when they opened the fire compartment. And so we did have heavy smoke, very low or no visibility on the fire floor, and heavy fire as they made entrance. And so it was an excellent training exercise for the departments who joined us in the event, and we had over 13 departments who joined us on the experiments. And these are those departments in the D.C. metropolitan area. We put over 6,600 firefighters through a multi-unit drill in this high-rise environment. And so many of them obviously coming more than one day, but over 6,600 firefighters participated in these experiments from these metropolitan departments. So to get to the results, which I know that's the most interesting part, give you a little orientation on how to read the graphs and how we actually made the time-to-task measures throughout the experiments. First of all, we measured what we called the go-to-work time. The response times, as you can see in this graph, and all of these graphs are in the report, the written report that we'll be going over later this afternoon in another workshop where we can get to a lot more detail. But what you're going to see here is from the time of ignition, then we measured, obviously, the recognition, someone calling 911. All of this was done up front with some assumptions and literature review. And then once the dispatch took place, we began the modeling. All of this was modeled through GIS experimentation, and we used our Geographic Information System at the IAFF to model the response of the closest units into the actual address. And so this would have been a very real response into that building that I showed you on a previous slide. And so with that being the case, then we were able to measure then as the units arrived, their time of arrival, engines and trucks, and where they would have to be able to stage the vehicles. Because as you know, with this multi-unit response, you run out of parking area or staging area very quickly. And so we began to then add in the times that they would take them to assemble their equipment and walk to the front door, to the lobby, and be able to make entrance into the building to go to work. And so with that, this is how we measured, and that's where you're going to see us continue to measure the time to task. Reading the graphs then, the bar graphs that I'm about to show you, the length of the bar has to do with the duration or the time that it took to complete each of the 14 critical tasks. And so the start or the bottom of the bar is the start time for the task. The top of the bar obviously would be the end time. And then the graphs that you see at the bottom are the times for the 3-, 4-, and 5-person crews. And so as we go through these, I'll point out some of the times and the specifics that you can see on the graphs that are before you. To show you the pattern, the attack pathway into the fire floor, once the crews ascended, they ascended to staging on the 8th floor, 2 floors below the fire floor. And as they made entry then to the core of the building, they were to pass through, stretching a line. All of the experiments used a 2.5-inch line. The fires were deemed large enough, and we'll show you that through the modeling, but the fires in this building were deemed large enough based on fuel load that they would have required 2.5-inch lines to even begin to extinguish the flames. And so we had the crews stretch 2 lines. The lines were used. We could not flow water, obviously, in the building as well, but we used sand-filled 2.5-inch lines. A great idea from one of our fire instructors. We were trying to simulate again the weight of the charged line, also the maneuverability, their hose handling of the crews through that interior core down to the fire compartment. And so that's how we simulated the charged lines. And so they would leave that inner core, stretch down through the elevator lobby, and make their way over to the fire compartment. You can see the location of the fire. And once they then entered the fire compartment, they would continue to be timed until they got water on fire just inside the compartment, and then to continue to stretch the line along that path. Now, for the fire to be deemed out, again, we were using simulation here, so the fire to be deemed out, both 2.5-inch lines had to be stretched to a threshold. And so both the attack line and the second line had to be brought in and brought all the way to a threshold that was on the floor at the seat of the fire. That would be deemed fire out. Now, once we overlaid these times with what you're going to see in the modeling, this was where it becomes very telling. So we had to back into our fire out times so that you understand the science when you try to explain it again. Jason will get into more of that when he talks about the modeling. And so the attack line, let's look at the results on the 3, 4, and 5-person crews in the attack line. Now what we see here, again, the bottom of that bar is your start time. And so you see some differences in the times there in the bottom row. And so some differences as they progress. And all of these results that we'll be showing you today are all statistically significant. Again, there's much more than we can provide here in the report, but we'll talk more about that in the workshop this afternoon. And so these times, as you can see, the start time, very relevant, because the 3-person crew, for example, as engine 1 comes in, they leave the driver at the hydrant, so he's hooking up. We have an officer and a firefighter who come in. Certainly they can't begin to stretch because one of them's got to stay in his lobby control. So this firefighter that was on engine 1 then had to wait for engine 2 to arrive before they could assemble an attack crew. So this is part of the delay, and this is where we're going to begin to see that crew size on those early arriving crews changes your tactical opportunity. It changes how you are able to deploy and the tactics you're able to use and the times in which you can engage based on crew size. That's why in the video you heard that sending smaller crews and sending more of them is not as good as sending larger crews early, because your tactics change. The time to intervention changes based on having to wait to assemble enough of an effective firefighting force to be able to move even the attack line. And so you'll see this more and more as we progress through the results. So attack line, and you can see the fire out times that are there. Let's take a look at the second line. Again, the second line now, where it is the engine 2 on the larger crews, they can begin this second line. It is a later engine arriving to begin it on the smaller crews. And so again, tactical changes in when we can actually deploy, when we can actually move these lines as the crews arrive. And so again, the 5, 6-person crews, you see they got a much earlier, the bar's lower on the graph, and so a much earlier start time. And then their completion time of stretching that second line there, you can see several minutes difference, a good 5 minutes difference on stretching that second line. And so looking at the fire out times, you can see the duration on the bars substantially different, and again, statistically significant between the 6-person crews and even the 5, the 4s, and the 3s. So even though they started in what appears, they started relatively early on the 5 and 6-person crews, but look at even the duration there on stretching these lines. And then the fire out, as I told you, both lines, the first and the second line, had to be in place across that threshold for them to be deemed fire out. Let's move then to search and rescue. Looking at search and rescue, this is the 10th floor, your fire floor. And so where we built in all of those cubicles, there's actually a pattern. There's an inner ring of cubicles and then an exterior ring of cubicles that had to be searched. There were over 90 cubicles here that our crews had to search. And so as they made entrance, as you'll see in that lower right corner, there's a green symbol there. That's where they started. The same entrance as the fire crews, right? So truck 1 is their first search crew. They're going to go up and begin to search. They're going to make the same entrance there as the fire crew. As the fire crew turns to their left to begin suppression, the search crew is going to turn right to begin their primary search. And so as they begin there, then this is a completely crawling search because there was either very low or no visibility until we could get the fire out in this area. And so there's all a crawling search. There's a victim, as you can see in that upper left-hand corner. There's a yellow star. That's our victim. The victim was always in that spot. And so depending on how efficiently the crews could search, that depended on, again, how they found the victim. And so I'll just tell you here again, truck 1. Truck 1 comes in. They have a 3-person crew, for example. They had to leave somebody, the driver, in the lobby for pressurizing the stairwells. So they left him with fans in the lobby. 2 persons went up, the officer and a firefighter, to begin the search. And so as you can see, only 2 persons. They're only going to be able to start that interior row. As the larger crews then went up, even the 4-person crew, leaving the same driver in the lobby, only goes up with 3. Still, they cannot split up. And so they're only able to start that interior circle of cubicles. But if we get to a 5-person crew, leaving the same driver in the lobby, they go up with 4. They're able to immediately split 2 on the interior, 2 on the exterior, and they're much more efficient in moving. So once again, just like on the attack line, we see that your tactics can actually change based on the arrival of a larger crew. And you begin to see this is not rocket science, but it does give us now quantitative data to be able to describe this much better to your decision makers. And so your tactics literally change based on the arrivals of your earlier crews, larger crews. And so let's look at some of the data and some of the results. As we see here on the 10th floor, this is your fire floor. Look at the start times, even though they're relatively the same, because as I said to you, truck 1 is always going to go up and start the search, regardless of the number that they're going up with. So they all start relatively the same time. But look at the duration of these bars. Look at the time, if you can see the middle row, and then, of course, the end times that are there for you, from 33 minutes on the 6-person crew, and even 36 on a 5, to over an hour on the 3-person crews. And so this is the way that they were deployed, and what you might imagine is the same thing for victim rescue. And so you'll see that the victim rescue, and when they were able to reach that victim, always located in the same place, is very different for your larger crews versus the smaller crews, and when they were able to get to that victim in the exterior cubicle ring. Let's look now at the floor above the fire. In the floor above the fire, we did have some smoke breach, but no fire on this floor, but heavy, heavy smoke. And so in this area, still we have some very low visibility, and so they're going to do a good portion of this crawling. If you can see in the diagram, the dotted lines indicate where there was no visibility, and they were doing crawling searches, versus the solid line where they had some light, good visibility, they were able to walk here. So this floor, as I said earlier, is a series of conference rooms, larger areas, and then closed offices with doors. And so the same thing, this floor had a victim, and so as they moved throughout, the effectiveness of their search and when they were able to reach the victim. So let's look at some of these results. Search and rescue on the 11th floor. You can see again starting at relatively the same time, but based on the same situation that we had with the 10th floor searches, these crews were going up intact. So this was truck 4 in every scenario. So truck 4 is going up and they're beginning the search. And this is where we see them being able to move efficiently based on their crew size and how efficiently they move the search. So even on the 11th floor, we see substantial differences on the completion of the search and rescue in the time frames that are there. Victim found, when they were able to find the victim, again, based on how efficiently they were able to move those searches, based on tactical changes, again, whether they could split off into 2 search crews or they had to remain as 1 based on crew size, again, how efficiently they were able to search the floor and find the victim. Almost a half hour, once again, differences in when they were able to reach this victim. Now, where this is going to matter is in just a moment when you see the fire modeling and what was going on with the fire growth at this same time and what was happening with the tenability that would have been on this floor and whether or not this victim could have survived based on when these crews reached them. Okay? So that you'll see that very shortly in the fire modeling. So let's take a look then at crew size and ascent mode. You know, as I told you, we looked at stairs versus elevators. Well, it was statistically significant that stairs and elevators, we did see a difference. Crews that used the elevators to go to staging, the 8th floor, 2 floors below the fire, much more efficiently reached that area than crews and were able to move more efficiently than crews that used the stairs, obviously going up. Again, not rocket science, not something we didn't already from your experience know, but now having the science, the empirical data, as the General President likes to refer to it, the empirical data now to inform decision makers. We can now show differences even in your ascent mode. So let's take a look then at that alarm size. Is it better to send smaller alarms or larger alarms? Does it matter? Well, the truth is that once we've been able to measure this, we can now see that on those, the fire floor and the activity that was going on the fire floor, we did not see statistical differences in the alarm size. But you might, if you'll reason with me here for a moment, the floor above the fire, if you remember the low alarm size is 3 engines, 3 trucks, right? The high alarm was 4 engines, 4 trucks. Well, as I told you, on the floor above the fire, who was going to work there? Engine 4, truck 4. And so where it is relevant is getting your operations going on the floor above the fire in the protocols that we use, which again are very similar to a lot of the metropolitan protocols because that's where we modeled them in the US. And so that fourth engine, fourth truck, getting your operations going on the floor above the fire, it was very relevant. And so the alarm size did matter in those cases. I want to show you this. This is actually a series of 4 slides, and I'll describe what you're seeing here because you can't read it, but watch the bars. Because these bars are going to show you the 14 critical tasks that I mentioned to you. And again, we'll go into much more detail this afternoon in the workshop, but watch the length of these bars and the color changes, because what you're seeing here is the 3-person crews, and the length of the bar here is the duration. And every time you see a color change, that's where they had to call for a relief crew because the task was not completed, okay? So by crew size, watch what happens to the length of the bar and the colors that are showing you how many crews actually had to go up to relieve in order to complete the task. So this is a 3, 4, a 5, and a 6. Let's do that again. Okay, a 3, 4, 5, and 6. And so that becomes very telling when you can see the tasks that had to be completed, when you can see the numbers of crews where you had to have relief crews go up to complete the task. And so with crew size, this becomes very relevant to the tasks that had to be completed in this high-rise, high-hazard environment. Let me tell you just about this chart, and then we're going to move into the fire modeling. With the time-to-task comparisons, we have charts that are in the report for you, and again, you'll get those reports. We have brought toolkits with us with a lot of the materials that you will need to take back with you to use this particular study. But in this chart, we have a series of these. This one happens to be just on the overall time to task, and I want to tell you how you read this, because all of this is, we have several charts on search and rescue, we have some on the fire out time, that are all relevant to crew size. And the way you read this is, if you were going from, and let's just look at the 5-person crew, if I had someone proposing that I'm going from a 5-person crew, read across the top, you see the 5-person crew on that bar, and they're saying we're going to cut you to 4-person crews. You see 4 persons then in the vertical, drop down and you see the negative 21.6. That says that's the efficiency you're going to lose. If you go from a 5-person crew, drop to a 4-person crew, and the overall time to task on a high-rise environment, your efficiency is going to drop by 21.6%. Same thing if I were to grow from a 3-person crew, let's say, to a 4. Okay, so again, look at your 3-person crew here in the vertical, right? So in the 4-person crew, 4-person crew in the vertical, 3 across the top. You see that 19.2, that's a positive, okay, right there. Your 19.2, that's what you're going to gain. If you go from a 3-person crew to a 4-person crew, you're going to pick up 19.2% efficiency. And again, we'll have this by task in the report. Now, the reason these are different, you're going, why is it different? Is because you're starting with a different denominator, okay? So if I start with a different denominator, I actually lose more by dropping a crew size than I gain in adding sometimes, because the denominator changes, okay? So that's how you'll read these reports or these charts in the report, and again, they'll be there for all those critical tasks. Now I'd like to ask Jason to come, and he's going to show you how we took the time to task, overlaid it with the actual fire and what would have been occurring in this high-rise environment and how it makes a difference. Jason?
Thank you very much, Lori. It really is an honor and a privilege to be able to come and share these results with you today. What I hope to do is take what Lori just talked about, which is the time difference of various response configurations, and translate that into actual meaningful service delivery outcome differences. Before I do that, I'd like to acknowledge a couple people who were instrumental in helping out with this. First is Craig Weinshank, my colleague at NIST, and Ray Ranalone from WPI. And both of them were very instrumental in helping us get to this point and are here with us today. So the fire modeling allows us to extend what we see from the time-to-task experiments. And to do that, we need to characterize the nature of the fire and how it changes as a result of the fire department intervention. So we start with characterizing the fire growth, its heat release rate values, and the fractional effective dose. We had 3 different fire values that fire growth rates that we used. And fortunately, the Society of Fire Protection Engineers has standardized these. We can characterize them as slow, medium, and fast growth rate fires, because as we all know, not all fires grow at the same rate. So we want to begin to characterize and bound the kinds of fires that we see on the fire ground in the context of the fire department response. Just as context, Dan did a great job of showing what a 1 megawatt fire looks like. It's probably a small upholstered chair burning at its peak. The slow fire, as defined by the Society of Fire Protection Engineers, is going to take 10 minutes to get to that 1 megawatt point. Our medium fire will take 5 minutes, and our fast fire will take 2.5 minutes to get to that 1 megawatt point. Okay. I'd also like to talk a little bit about sprinklers, because you can't talk about high-rise and not talk about sprinklers, and what that means to the safety of our firefighters and the outcomes on the fire ground. So the next 4 slides, I hope will speak directly to all of you, the firefighters, because what I want to do is demonstrate using a variety of different methods exactly what the hazard to our fire service is based on our response configurations. So here we have a table that looks at the 3 different fire growth rates, slow, medium, and fast, and I'll talk about medium, because as it turns out, when we look at how the way typical combustibles burn, particularly the kinds that we may see in commercial buildings, medium is a pretty good approximation of the speed of which we would anticipate these fires growing. If we look at our bounding response configuration, so our slowest configuration is going to be our 3-person crews taking the stairs. That's at the top of the graph. And these are rank ordered all the way through our fastest configuration. That's our 6-person crew taking the elevators. What we've done is we've used a concept, it's the total energy released in that fire compartment. So if we take all of the fire energy, we add it all up, that is a very good proxy for the hazard that the firefighters are facing. The tenability, the toxic gases, the products, the temperatures, everything that you associate with fire hazard scales very well with this kind of energy release. What we see is that in the 2 extremes, our 3-person crew taking the stairs has 7.2 gigajoules of energy released on that fire. Comparing that to our 6-person crew taking the elevator, we're down at around 3. Okay, that's a very substantial difference in the environment that these firefighters are operating in. Okay, on our next slide, we have the same data now plotted. And the advantage of looking at the data this way is we can now begin to look at the effect both of our response configuration, stairs versus elevators, as well as crew size. And you can see that for the 4 bars on the left-hand side, those are the crews taking the stairs, you get a substantial decrease in the amount of energy released based on whether you have 3, 4, 5, or 6-person crews taking those stairs. And the same for the crews taking the elevators. On the right-hand side, we get a substantial decrease in the total amount of energy, i.e. the total hazard faced by the firefighters when they're entering that fire compartment when they take the elevators. And then we can compare the left 4 versus the right 4 and see that the crews who take the elevators, because fire suppression is one of our early tasks, getting there to that compartment earlier, getting water on that fire, can make a significant difference in the total hazard encountered by our firefighting crews. Okay, so this is our water on fire time and fire out times. So these initial responding crews, remember we have 2 2.5-inch lines. We have the first engine crew getting water on the fire, as well as a second crew coming in behind, all pushing to the point where we get this fire out. Again, 3-person crews taking the stairs. We're looking at something on the order of 18 to 19 minutes to get water on the fire, and we're looking at about 28 minutes to get that fire completely knocked down. By contrast, our 6-person crews taking the elevators, our faster configuration, we're looking at about 12 minutes to get water on the fire and 19 minutes to knock that fire out. Interestingly, 19 minutes to knock that fire out really isn't too far away from where our 3-person crews taking the fire are beginning their attack. Okay, that's a significant difference. And I hope that really shows up here. This is a visualization of the size of the fire at the time that firefighting crews are entering the compartment. So as Lori mentioned earlier, our crews are entering from the sort of bottom right of the core. They're turning around and they're facing a fire. Well, if we have a 3-person crew who's taking the stairs, they're arriving later. And later on the fireground means bigger fire. You can see visually where that fire is burning and the magnitude of that fire as compared to our 6-person crews who take the elevator. They're able to get there earlier, and they're able to subsequently fight a smaller fire. But it's not just that they're fighting a smaller fire, they're fighting a smaller fire with additional crews as well. It's easier to do because they have more manpower fighting a smaller fire. So these are actually twofold types of differences that we're seeing when it comes to characterizing the hazard that you all are facing when you open the door to the fire compartment in the high-rise. Okay, I promised we'd talk about sprinklers. Sprinklers make a difference. It really makes a difference to the size of the fire that you face when you go onto the fire compartment. It also makes a difference to property loss, and it makes a difference to the hazard that the occupants in that fire compartment may be facing. When we look at the modeled response time of the sprinklers and the size of the fire at the time that those sprinklers would be likely to go off, we can see that the activation times obviously are slightly longer for slower growing fires. It takes a little bit longer for the temperature at the ceiling to get to that activation point. But it results in much, much smaller fires on the fireground when the sprinklers are installed and when they're maintained and are adequately designed to control that fire. We're going to talk a little bit about, at the end in our conclusions, about some context of how we want to think about sprinklered fires, but that's clearly a significant component of high-rise firefighting. Now I'd like to talk a little bit about what this means for occupants who may be trapped on the fire floor. Okay, and in order to do that, I need to introduce a concept called fractional effective dose. If any of you have read the residential fireground, this is the same construct that we used in the residential fireground. And it's basically a scientific characterization of the likelihood that people exposed to a certain toxic dose, in this case it's carbon monoxide, carbon dioxide, oxygen depletion, how likely is it that a person would become incapacitated? And by that we mean unable to effect their own escape. ISO, and this is the International Standards Organization, not the insurance services, has an international standard by which we can calculate hazard to occupants. And that's what we're displaying here. There are 3 basic thresholds. We have a first threshold for a sensitive population, so people who may have compromised respiratory or pulmonary systems. Elderly, young people who have smaller body mass, for example, would be characterized as our sensitive population, and that threshold is a FED value of 0.3. Mathematically, by definition, the standard has defined a 1.0 fractional effective dose as the median point. So 50% of the population will be incapacitated when exposed to a dose of FED equal to 1.0. And then we also have a certain segment of the population, for whatever reason, is able to tolerate a greater exposure to toxins and yet still affect their own escape. That threshold is defined as FED greater than 3.0. And we've got a color scheme here, and this color scheme is going to be important for the next few graphs. The blues are areas where it's unlikely that people receiving that exposure to the fire conditions would become incapacitated. So the fire department rescuing them in the blue area is a very high likelihood of a positive outcome. Yellow, between the sensitive and our median population. Orange is between that median and very sort of hardy, for lack of a better word, population. And red areas are going to be those areas where we would not expect a lot of tenability, a lot of survivability, even if the fire department rescues them, based on the exposure that the occupants received. Okay, so here's something that should look familiar. It's the 10th floor, and we've got 4 different displays of that. We've got our 3-person, our 4-person, our 5-person, and our 6-person crews. And each circle represents the time at which the fire department crew got there and was able to effect a rescue. And we know, based on the times that Lori talked about, the arrival times, and now adding into that our fire modeling, we know the total exposure for the person based on the time that it took the fire department to get there. And therefore now we can visualize the likelihood that that person would have a positive outcome, okay? So blues, remember, are goods, yellow, orange, and red in that order. And what we can see in the upper left-hand corner is for our 3-person crews, we've got lots of yellows and oranges. So we've got people who are receiving significant exposure to this medium T-square fire, okay? As we move through 4-person, 5-person, and 6-person crews, our fire department crews are getting there earlier. They're getting there earlier primarily because what Lori talked about. Tactically, with additional crews, we can improve the outcomes because we can operate differently as a fire service with larger crew sizes than we can with smaller crew sizes. And that means getting there earlier. You can see particularly on the outside ring, when we can split and search in parallel, the outcomes for the occupants are going to be much improved because their potential exposure to the fire products on that floor is lessened. And in fact, by the time we have 6-person crews, you notice the preponderance of blues on our fire floor. We have much better outcomes for our 6-person crews doing search and rescue on that fire floor. Here it is looking the same kind of response configuration, but this time we're looking at 3, 4, 5, and 6 for elevators. You can see that for the elevators, our times, we have a little bit of yellow and blue for our 3-person and 4-person crews. By the time we get to 5-person and 6-person crews, taking the elevator, getting up there earlier in the fire, we can affect our rescues at an earlier time and have better outcomes. Okay. Here, as opposed to looking at the times that each of the individual occupants may have been rescued, we're going to have the tenability on the floor at the time that the search was complete. So remember, it took 3-person crews longer than 4-person crews, then 5-person crews and 6-person crews to complete that search. So this is the time when search was complete on the floor. What was that overall tenability? And this is a new visualization capability that we've added to our fire modeling, to be able to look at the holistic overall tenability on the floor. And you can see very clearly in the 3-person and the 4-person crews, we have substantial area of our fire floor that is in that orange regime, the greater than 1.0 FED values. We've got substantial portions in the yellow as well, between the sensitive and the median population. As we switch over to the 5- and 6-person crews, we can see that we've eliminated that 1 to 3 regime, and we've got all the people below that 1.0. So we've got a greater than 50% chance for pretty much everybody on that floor of affecting a positive outcome in terms of the occupant rescue. What I'd like to do now is show you a visualization. What you're going to see is what I just showed you on the last slide, how that fractional effective dose moves throughout the floor. In this case, we're going to compare our 2 extremes, our 3-person crew size to our 6-person crew size, and what that means as time progresses on the fire floor based on those response configurations. And you'll notice that these visualizations are going to occur both because we're able to do rescue, but also because we're able to turn off the pump. Fractional effective dose is a function of the fire, and to the extent that we can extinguish faster, we have better outcomes. We can also complete our search and rescue faster. So again, if we can show that one more time, what you're looking at there is the total evolution of fractional effective dose over time for the floors based on our 2 response configurations. There we go, one more time. You'll notice that initially they're going to begin very similarly, but as we're able to put out the fire and we're able to complete our search and rescue, we're going to get better outcomes. One more on the, there we go, perfect. And you'll see that we begin to develop that orange regime in the left-hand side of our 3-person. We've completed our search and rescue prior to the onset of those orange areas, those higher likelihood of adverse outcomes. Okay. The next slide I'd like to show you is one that puts our fire growth rates in context. So we have here a display of our medium versus our fast growth rates. We know that fires don't all grow at the same rate. In fact, Dan and Steve did a great job of talking about how we know that they're growing at a faster rate than ever. Okay? So this is what it means in terms of the kind of fire that you would expect to see on the fire ground based on a medium or a T-square or a fast T-square growth curve. And we're going to see substantial differences based on the identical response configuration. The only thing here that we're looking at differently is the fire growth rate. So since you don't know, as you're entering into that environment, what that growth rate is, you need to be prepared as the fire service for the kind of the worst case scenario. We need to staff, and we need to prepare, and we need to train such that we're anticipating and ready for these more significant scenarios. And here you can see we have very significant adverse outcomes for that fast growth rate fire. On the bottom, we have more positive outcomes because we have the same response configuration, we just have a different set of hazards. We also looked at the occupant evacuation because we want to know, how is this interacting with our fire department response? And we looked at two basic different configurations of our evacuation. The first is if we had 100 occupants per floor. And as we looked at the architectural drawings for the building, that's about what this building was being operated at in its former life. But we also looked at how would the building evacuated if it had something that would still be allowable by code, but would be a higher density of occupants, 200 people per floor. And our findings were that, not surprisingly, more people per floor, longer evacuation times. In fact, longer evacuation times that substantially overlap with our firefighter response configuration. So we're operating as a fire service concurrently with some of this evacuation that's still going on. We also looked at what if some of the occupants were allowed to use the elevators, occupant evacuation elevators, in addition to fire service access elevators, two new code provisions that will both speed the response time for our firefighters, and we've shown now what that means by firefighter elevator use, as well as reduce the building evacuation time for our occupants. And we can see that we can get significant improvements in the occupant evacuation time if we allow 25% of the occupants to go ahead and use those elevators. I'd like to very briefly mention, and we have Dr. Denise Smith with us here today, that there was physiological monitoring looking at how the firefighters were working on the fireground. We're not going to talk about that here today, but that report will be made available in the future as well. So our first conclusion is that when responding to that medium growth rate fire on the 10th floor, 3-person crews ascending the fire floor confronted an environment with 60% more energy released. And remember, energy is a proxy for all things bad. Energy is related to that tenability, the toxic environment, the amount of CO2. It's related to the temperature that the firefighters are operating in and the temperature that the occupants may be exposed to. Larger fires basically expose our fire service and expose occupants to more adverse conditions. And crew size and response time can have very positive outcomes when we look at the data. Second, these larger fires produce exposures for our building occupants. We saw that as we looked at the rescue times. We saw that as we looked at the overall tenability on the floor. Larger fires result in more adverse outcomes. And larger fires, again, are related to our ability to get there and actually suppress that fire, as well as our ability to get to the occupants and rescue them in a timely manner. And finally, I want to talk about sprinklers. A properly engineered and operational sprinkler system can have a very positive impact on the hazards faced by our fire service, the hazards faced by the occupants. But we know from National Fire Protection Association analysis that 40% of all buildings that we might respond to in these configurations are not sprinklered. And we know that sprinkler systems fail in about 1 out of 14 fires. That's 7%. So we need to recognize that sprinklers can save lives of firefighters, lives of civilians, but we need to be prepared to respond to fires in an unsprinkled environment, not only because of the prevalence of unsprinkled buildings, but because of the possibility that the sprinkler system won't be functional. And hopefully the results that we shared with you today will help prepare you to make adequate response configurations in the best interest of firefighter safety, occupant safety, and property loss. Thank you. Thank you very much. job.